Thank you. I'm happy to present our work that I did together with Christian Knoflach from Bartenbach. He did a huge part of the work. Unfortunately, he cannot be online and with us today, so I give the whole presentation on my own. Great to be here again. Great to see all of you again. I'll present some work. It is a follow-up on the work that I presented 2 years ago. We started with that, and Christian presented the intermediate step last year. So that's like the final presentation on that. It's about the DGP work that we did, thinking about how does DGP work for small glare sources, especially in the periphery. If you have small glare sources not in the central visual field, how does it work there? So what I'm going to talk about, a little bit motivation, why are we doing that? Why did we look into that? How did we develop the DGM, the daylight glare metric, how we called it, the modified DGP, the simulation evaluation, how did it show up, and also the subject study that was done at Bartenbach under the artificial sky there, and some conclusion. To begin with, what is daylight glare? I thought about, okay, how to start with that. Working on the presentation late in the evening, nobody in the office to talk to. Okay, you chat with somebody with some large language model. I asked, okay, what is daylight glare? We know that actually it's quite some proper description that came up here. There's discomfort glare, there's disability glare. It is a visual phenomenon. Okay, we know that. So I wanted to know more, not only what is daylight glare, why is daylight glare bad? Why do we need that, or why do we need to care about that? Also, that still makes some sense and is quite okay to read through: visual discomfort, reduced visibility, health impacts, and so on. We know all about that. Looking into the topic that we were looking for, DGP for small glare sources, how can we evaluate glare? So what can we use to evaluate it? So there's a long list that comes up: DGI, UGR, CIE glare index, vertical illuminance, you know, all that as well. So started to think about, okay, daylight glare with UGR, you can try it. We know you shouldn't do it. It's not the best idea to do that. But as we know, DGP is a good way and a good metric to do so. I also asked, is DGP a metric that is adequate to do that for small glare sources? And raising that, the next question, also here, strength of the DGP, limitations with small glare sources. So there, ChatGPT has an opinion on that. But it's an interesting one. Sensitivity to source size, DGP tends to be less sensitive to small, high luminance glare sources because it averages luminance over the entire field of view. It was new to me. And again, it proposes to use UGR, and it says UGR might be appropriate for evaluating small glare sources as it focuses more on the size and position of the individual light source. Although from UGR, we know that for small glare sources, you shouldn't use it. So that ended my conversation with this sparring partner. I propose something to read, something more reasonable if you really want to get into that. Just as a starting point, there's a lot of work out there where you can find out all the details and background information. Why did we start looking into that? Starting with evaluations that we did and working on the BSDF topic and a peak extraction from BSDF, you have like spread out your solar size into a Clem's patch, for example, or you extract the real sun size and then run the evaluation on that. So these three images on the left side, the Clem's BSDF, in the center, the ABSDF, so the sun extracted. On the right side, what then Greg and Towning did with the blur filter applied to mimic what the camera does, what was the basic for the development of the DGP metric. And if we look at that, what the DGP is, if we evaluate it for these images, we can get from 0.28 up to 0.5 if it's extracted directly, or if you use the blur filter at 0.4. So it's just in between perceptible and tolerable glare. So if you are a consultant to somebody who did the design of that, what would you say? Is it imperceptible glare? Is it intolerable glare? Is it somewhere in between? That's the question that we had and that we started with. Flashback to the presentation I gave 2 years back in Toronto. We started this evaluation in an IEA project where we had a round-robin test with a lot of samples, or 2 samples, but a lot of institutes generating BSDF data, and we compared this BSDF data and looked into how does the BSDF comply, how do the BSDF data sets match, and also how does the evaluations, if we use these data sets, how does that come out in the simulations. And doing that with and without peak extraction, we first came up with this, that we saw, okay, we have a good match in the vertical illuminance, so the general methodology of the peak extraction works. But the maximum luminance, of course, as we put it into the small sun size back in there, is way larger, and that causes the DGP to raise, as what Jan also mentioned first. We have the luminance squared and the solid angle only linear in the formula. So running a lot of evaluations on that, we thought, okay, we should look into that, and what does really make sense, and what is really the core problem that we are facing here. I said it's the luminance is squared and the solid angle is linear in the formula, which is also true for most of the other glare metrics that we know, which makes sense because this matches with the subject evaluations. But the question that came up, is this still valid, or is this still reasonable if we can't distinguish between 2 glare sources? So if we look into that a little deeper, taking a glass material and electrochromic glass, 2% transmittance as an example, and looking into that with the blur filter without filtering, we see that we really already here we decreased the DGP evaluation quite a bit, which was done to match what the initial camera-based evaluation and development of the DGP back then did. But then if we open the field of BSDF data to it with CLEMS or with tensor tree, in this case, the 4096 maximum resolution, we can see, and if we look through the numbers down here, the vertical illuminance matches pretty well, depending on if we extract the peak source or not. But if you have that, you can really select whatever DGP you want. So if you want to tell your client it's good or it's bad, depends on if you want to sell your product or not. We looked into fabric shades, and here, thanks to Tao Ning for sharing the data for a lot of different fabric shades. Data was measured, and also here, depending on the evaluation method that you use, the DGP results can vary very significantly, and so it's something that we really said we need to investigate further. Also for another fabric shade, same situation here. We then went on really trying to define, okay, what does that mean? How can we come over that, and how can we find a solution for that? Because the problem is, especially if we have a small glare source, and this is something in a discussion that we had back then in Bartenbach when I was still working there with Christian together, we often discussed, okay, is it really reasonable if I have a small glare source somewhere around here, and it causes some vertical illuminance at my eye? Does it really matter if it's like a teeny tiny glare source here, if it's a little bit bigger, if I can't distinguish it, if the same illuminance is caused on my retina, on my vertical illuminance in my eye? So this was the starting point for that work that we did there. So we said, okay, if we can't distinguish it, also that daylight glare probability or that glare metric that we use should be more or less the same. And this was the, yeah, as said, the starting point for our discussion. ChatGPT said you should use UTR maybe. I don't propose to do that, but in UTR, we know there is at least the recommendation UTR should not be used if it's a glare source that is smaller than 0.0003 steradians. So that's about 2 times 0.5 degree opening angle. So there's a limit in there because they exactly, or they know there's this L square omega issue in the formula that causes your value, your metric value to explode at some point. The CIE group that worked on that issue then and published that in the CIE report 147 proposed to replace this small glare source. If you have a small single LED point somewhere on the ceiling, you should replace that in the calculation with a larger area that matches this 0.003 steradians solid angle for the evaluation. So if you think of a typical office room, that means like replacing that LED point with a 8 centimeter sphere or 8 centimeter disc at the ceiling. So with this in mind, we did the first pre-study at Bartenbach with a high luminance, high dynamic range display, where we displayed different sized glare sources. So they were not glare sources, but they were like visual stimuli that we caused same vertical illuminance at the subject's eyes, and they were sitting there. And with 2 different experimental studies, we either continuously changed the size of this stimuli, or we showed 2 different sizes next to each other, and they had to decide which one is the bigger one, or are they equal size. So from that, we more or less just proposed the same modification that UTR and the CIE group proposes. So whenever it is beyond this threshold, replace it with something averaged over this threshold area. And this is what we tried to find out with these studies. So that is the results plotted for these. We had vertical angles, horizontal angles tested with the subjects there. And we tried to find out, okay, what is the threshold angles where people just cannot distinguish anymore which one is the bright small stimulus and which one is the darker but bigger stimulus. So from this, we came up with a somewhat weird, but it is, if you use like, it's a little bit the same with ChatGPT. You can also use this Turing bot software. So it just you throw in data and it gives you a formula that gives you a nice continuous function, which makes sense at some point, but it's something that you cannot reasonably describe why you use that. At the end, that's the formula that comes out from that fitting, and that gives us these threshold angles where in the visual field of view to use which angle as a threshold. We did that for the experiment data that we had and added a scaling factor, more or less aligning it with the CIE recommendation of this 3 times 0.003 steradians. That this is something where we said, okay, this is established for glare evaluations for small glare sources. This is our first guess for this scaling factor that we introduce here. So the threshold angle in the visual field, this is what comes out here, together with this scaling factor that we introduced, this 2.346. So as you can see here, in the central field of view, this is where we limited to this 2 times 0.5 degrees, what matches the UTR recommendation. And as you approach to the peripheral field of view, this threshold angle increases up to around close to 6 degrees. So we said, Okay, let's go back to the simulation and have a look. What does that mean, and how does the evaluation, how does the DGP numbers change if we apply that to our renderings, our simulations? So we set up this test scene that's more or less mimicking not the office space, but the facade orientation and the time where I started doing the simulations in my office in Innsbruck. On November 15th, I sat there looking east and said, okay, what would happen here? Took 3 different time steps with where you see the angle from the viewing direction is between like 45 and 75 degrees. So it is really in the periphery of the view where you see the sun penetrating through the facade. I evaluated that for 2 different settings. Once for an electrochromic in different tint states, and then for the different fabric shades that Towning provided me with. So we had all the tint states that we found from back then Halio webpage, but just modeled as a glass with these transmittances and as glass material or as clamps and as isotropic tensor-tree material. The second part with the fabric shades, we had these 11 data sets from Towning in clamps and in anisotropic high resolution as well, and we went through all of these as well. So looking at the results, this to explain like the data that is plotted here, we have always 5 groups of data sets. It's the for the electrochromic glazing, it's the on the left side the glass material modeled as glass modifier, then the clamps with BSDF modifier, clamps with ABSDF with the peak extraction, tensor-tree, and tensor-tree with the peak extraction. And the 4 bars are DGP, the classical one, DGP with the blur filter applied, the new daylight glare metric, and the daylight glare metric on the image where we applied the blur filter before. So going through these 3 hours, these 3 times, we see that the new metric like levels the outcome, and especially what we see with the blue bars, they're overshooting. That means whenever we have the direct sun in the field of view, we have a very high value reported that is already significantly reduced if we have the blur filter attached first, but it is even more reduced if we average, and this is because we average more than this blur filter with the around 0.18 degrees thus we average more. So we level out these details. So that's at 9 a.m., 10 a.m., and 11 a.m., where we go even further to the periphery in the field of view, and you see that it is leveled out even more in these areas. Similar results for the fabric shades. We don't have here the material as a reference case, so we only have BSDF clamps and tensor-tree with and without peak extraction. And also going through here, it's the same picture where you see that we level out these with the scaling and with the averaging in the periphery of the field of view. First findings from the simulations, the DGP varies significantly depending on the glare source size. This is what we know and what we know from the formula and from the results. The DGM stabilizes that results. Clamps without peak extraction is not sufficient for doing glare evaluation. It's also something that we know from the past. With peak extraction, we still may run into issues because we take all the energy, all the light that is in a single clamp patch and reduce it to the sun, which then also includes all the circumsolar scattering. So it might even overestimate what we have in the direct sun. So this is something that we still need to work out. When does peak extraction best work? So what is the best resolution in BSDF data to be used with peak extraction methodology? and also from this scaling and this stabilizing and like averaging out the results, this is something we said, okay, also this minimum solid angle, we really want to have more data to focus and to fine tune these results. The second part, in the subject study in the artificial sky at Bartenbach, the artificial sky dome, it was said to have a vertical illuminance, a background illuminance of 1000 lux at the subject eyes. And with the LED sun that you see here in the image, different scenarios were defined and were simulated. We had 35 people answering the questions and doing the study results. There that's some descriptive statistics in there, different ages, different eye colors, self-reported bright light sensitivity. And so that's the cases that we showed to them. Different angles, different positions in the field of view where we had the sun, this glare source positioned. And we varied between different sizes and different luminances. So it went up to 6 million candela per square meter for the glare source. And we changed the source size between 1 and 3, around 3 degrees opening angle. And the situations were always designed in a way, you can see that from here, that's analytically calculated values for DGP and DGM, only from the defined sources that we have DGP varying, and DGM is stable, or it yields the same results. So this was our hypothesis, that people cannot distinguish these situations. The questionnaire, it was different questions around, are you feeling glare? Are you disturbed by glare? Yes or no? How much are you bothered by glare? And looking into these questions, especially 1 and 4, we evaluated, I'll show later, how would you describe the current glare? According to the four categories: non-perceptible, perceptible, disturbing, and unbearable, so intolerable, or how much are you bothered at glare at the moment, from 0 to 10. And looking at these results for these situations, for example, here in the very periphery, 70 degrees azimuth angle of the sun, we see that the DGP increases with smaller but brighter light sources, and the DGM. So this is also how we designed this test. And the results, or the responses, they really show that there was not a significant difference in the responses from the subject. There were also other interesting and still not really or findings that we could not really answer yet. Like in the situations 1 to 4, we see again a significant difference in DGP, but not in DGM. But the responses by the subjects, they were even contrary to what DGP says. So DGP was higher for situation 1 than for 2, but the response was the other way around. So this is still something we don't really know why that is like that. Some evaluation, yeah, basically what I just reported. So concluding, a couple of points. What we see as advantages of this modified metric is that glare from small glare sources from the sun, if they are in the periphery, they are not overestimated. The second, and maybe also important thing for changing a metric that is well established, and the DGP is so, I don't criticize DGP per se. It's a highly it is a reliable and a good method, and there are small things that need to be even increased or need to be need to be better. So a benefit maybe, or for sure, is that it doesn't change the existing metric for situations where we don't have small glare sources. This is something, whenever you change something and people rely on something on it's a well-established and known metric, and it's even standardized. It's in EN 17037 in the European metric already. So like as a comparison to what Constantus did 2017, also they tried to find out sun in the field of view through window shades, but they changed the metric at all. So they did a new regression on the whole model. And this would change all the DGP evaluations for existing situations as well. Another benefit might be that you don't need to do post-processing on the luminance image because it is done through the metric itself that you average over that glare source. And as a general conclusion, as I also mentioned before, is that we still need to do fine-tuning and need to find out a better, probably a little more accurate scaling factor that gives us the threshold angles in the different areas of the field of view. So that's also a call to everybody who is interested in doing glare research whenever there's data available or there's new research going on. Also thinking about this modified metric, looking into it, challenging it with new data, and try together with us to fine-tune this scaling factor. That's it from my side. I'm happy to take questions. Right.
Great. Did you back up a few slides directly for your solution? Right. So what about the situation? By the same formula for those?
Yeah. Yeah. So there is this small averaging. When we're close, so that the threshold angle is pretty close to that UTR threshold. And as we see here, so there is this averaging. We have like for the situation 1, for example, DGP report 0.53, DGM 0.47. So there is already some averaging. But the interesting thing is that the response really were the other way around. So people said, okay, it's even bothering more. But we do the same disk replacement here. Yeah. Look. Yeah, so this is we don't do like the same size everywhere. This is like threshold angle that where's it? That one. That is also defining if the glare source is in that area, we replace it with this size. Yeah, so it's like the subject studies, that's the situations that we looked into. That it's the azimuths of the sun from 0, 20, 45, 70, and the gamut was 40, 35. So it's the position more or less on the right side where we had. No, not at the very end of the. That's something where we say, okay, yeah, we might try that, but it's always, do you try, or how well does a metric work for a glare source where you will never look at?
So have their sort of
Jan, go ahead. Jan, go ahead.
Yeah, thank you. David, we discussed already a bit in the past. I'm still wondering what the physiological background is of this change that you propose? Because basically, if you look at the retina, there is no blind gap except the little one that is well known, but the rest means everything is covered with photoreceptors, and basically what this means is that you say that the response is different if you go to the periphery compared to the other part, and I don't know what is the reason for this, and the other. So maybe you have an explanation for that, and the other thing is that well, we discussed this already, that using our data that we have from our electrochromic study showed that this change that you propose is actually too much. It might be something that is according to the scaling factor, but yeah, I don't know if you had worked on this in the meanwhile. And the third question is, have you done also, that would be the ideal case here, also like pair comparison for the subject. So basically changing the size and following your hypothesis, yeah, that it should have a different response, and then you let the people do a pair comparison, which one of the situation causes more glare, or if it's the same. Have you done this as well, or you're just using this scaling if there is discomfort, and then on a discomfort scale?
I try to remember all three questions. The first one, the physiological idea or behind that is also looking into brightness and expect, or the brightness that you experience from stars. It's only based on the vertical illuminance, so that magnitude that you see that. And that's where we thought, if people cannot distinguish if a light source is bright or small or large and darker, so there, it seems like there is something people, even if there is the retina is with all the receptors there, if they can't distinguish it, it seems like, okay, then also the glare might not be a different one that is expected. So that was the first thing. The second one was, what was the second question? Yeah, too much. Yeah, and that's for sure. This is also what I said when showing the results from the simulation study. We might overestimate it with that. We fitted this to our experiments and added the scaling factor to come up with something that is similar to what UTR proposes. And this is why I really call for experts to do more evaluations and more studies to fine-tune the scaling factor. So if we can do that with your electrochromic data, that would be perfect. And on your third question, no, we did not do that pair comparisons. We did raise these questions that we showed and ask people if they are experiencing glare or not, and if they are bothered by the situation or not.